Hello, my name is Marco Aurelio, and in this video, we're going to talk about relative stability. Relative stability is going to indicate how close a system is to instability. For this instance, Nyquist plot and butter plot are going to be used to explain this topic. It's important to know these kind of indicators in order to see how much we can change a system before it gets an unstable behavior. A Nyquist plot is a diagram where the points plotted represents the magnitude and phase of the open loop frequency response, corresponding to a particular frequency. In order to build this kind of diagram, we need to know the functions of magnitude and phase of a system that depending on the frequency. So the point is going to depend on the phase and gain at a given frequency. For example, at frequency 0.72, we're going to have a phase of minus 180 degrees and a gain of 0.49 value. In this graph, in order to avoid instability, we need to avoid at all costs this red point, which is minus 1, because at this point we're going to have an unstable system. So what is a baud plot? Here we have an example of a baud diagram, which is going to be a graph specifying the gain and phase of a system across the frequency spectrum. Here we see that the gain can be expressed in decibels as well as an absolute value. So what are these values going to tell us? The gain is going to tell us how much the magnitude can change from an input signal to an output. Here we see that the gain in this case is going to be 5, but we can have an increasing value as well as a decreasing value. So take note of that. And the phase is going to tell us how much this graph is going to be shifted compared to the input signal. In this case, we're going to see that this cosine wave is going to be shifted p divided by 2 radians, converting it like a sine wave. So we need to take note of the change of both values because it's going to tell us how the output of a system is going to behave depending on the input signal. A margin can be described as an extra amount of something you can use if needed. Gain margin and phase margin are going to be extra that will protect the systems to be unstable. If a system has low margins, it is considered less stable because low variances in the system could easily cause instability. So what makes a system unstable in the first place? Let's consider the open loop transfer function g of s. So the system is going to be unstable when the poles are in the right half of the plane. But right now we are working with closed loop systems. So what open loop characteristic makes a closed loop unstable? So let's consider the same open loop transfer function and let's close it with unitary feedback. The new transfer function is going to be g of s divided by 1 plus gs. In order for this system to be unstable, we need this bottom half of the function to be 0. So by that we get that g of s needs to be minus 1 in order to this system to be unstable. So we need to keep the open loop system away from minus 1 and our closed loop system will be stable. So what does the gain and phase margin is going to tell us? Right now, if we want the system to be equal minus 1, we need a gain of 1 or 0 decibels because it doesn't scale the output by any factor. And we need the phase to be minus 180 degrees because it's going to flip the input upside down. So if the system is both 1 or 0 decibels of gain and minus 180 degrees of phase, is going to be this -1 value. So the gain and phase margin is going to tell us how far we are from that point and of instability. So how can we find these margin values in a block diagram? Here we have an example of how we can get a phase margin. First, we're going to get the crossover frequency, which is going to be the frequency value at which we have the value of magnitude of 0 decibels. Then we see what is the phase value at that point of frequency, and in order to get the phase margin, we need to do a simple calculation, which is going to be 180 plus the phase value at that frequency, which in this case is going to be minus 169. So the phase margin value for this case is going to be 11. Now, to find the gain margin, we now need to know the crossover phase frequency, which is going to be the frequency at which we're going to get the minus 180 phase, and we need to see the gain value at that frequency. So the difference will be the negative value at that point. So now the gain margin for this example is going to be 3.68. In MATLAB we can easily find these margins precisely by clicking that option. And now we can see that the margin is very close to what we got at 3.74 decibels, and the gain is going to be 10.7 degrees. Now we're going to find these margin values in the Nyquist diagram. First, we're going to find the gain margin. First, we're going to see what is the magnitude value at minus 180 degrees. Here we have that the minus 180 degrees will be in the axis, in the real axis. So the magnitude will be 0.648. Now, in order to get the value in decibels, we need to apply the logarithmic of this value and then multiply by 20. So here we have that the gain value in this case is going to be 3.76, really close in which we got in the both example. For the phase margin, we need to see at what point we hit the unitary circle. In this case, this will be the location in which we hit the unitary circle, because this is the one of magnitude. So, because if we are in the third quadrant of the plane, in order to find the phase value, we need to do this. We need to find what is going to be the phase at that point. So we're going to divide the real part, the imaginary part, 0.186, divided by the real part. Then we're going to apply the inverse tangent, and we're going to find that value is 10.71 grades. To find this value to find the real phase value, we're going to subtract. We're going to sum this value with minus 180. So we're going to sum the value we got in the inverse tangent. Here we have that the value of the phase in this instance is going to be minus 169.29 degrees. So in order to find the phase margin, we need to sum this value 180, and we're going to find that the phase margin is going to be approximately 10.71, which is very close to the one we got in the both example.